Hey everybody, welcome to the channel. Here we have another video on Module 2 Dynamics, this time a block on an inclined plane subjected to a number of forces. So this example is quite tricky because you'll notice that this force here is at an angle on the plane, and the plane itself is on an angle to the horizontal. So this question comes in as a special request from Joey. It's a 4-part question. Let's take a look at how we might approach something like this. So the first part asks us to calculate the resultant force on the object. Now, we know that every time we're asked to calculate the resultant force, what we are being asked to do is we're asked to do the summation of all the forces. So I'm going to be calling this force F1, this force F2, and let's take a look at what forces aren't shown. We aren't being shown weight, and we aren't being shown the normal force. So apologies for the line not being straight. And I'm just going to use N for the normal force here. Okay. So realistically, what this question is asking you to do is it's asking you to find F1 plus F2 plus W plus N. So it's easy to forget about the N force, the normal force, because you might not be used to seeing it, but the normal force is present whenever something sits on, say, like the ground, or in this example, a plane. So it always acts perpendicular to the plane. Now, how might we approach this question? Okay, so we can take a slight shortcut to speed up this process. Okay, so the shortcut I'm going to be using is going to be listed in the assumption. Okay, so the assumption we're going to make is 1, no friction. Okay, so no friction is implied in this question because there was no mention of a friction coefficient. Okay, so that's not really the shortcut I'm talking about. The shortcut is really in part 2 of my assumption, that the block slides along plane and doesn't lift up. It doesn't lift up. Okay, so this assumption is that even though you have a force that's lifting up this way, you make the assumption that because of the weight, you're not going to be actually lifting up above the plane. It's actually just going to be sliding along the plane. Okay, so I make this assumption. Now, the next thing we need to be doing is we need to be setting up the axes that we consider positive and negative. So you would have probably done this by usually considering x and y to be positive and negative. So the reason why we're not going to be using x and y is because it's more convenient to be using the parallel. So this one I call parallel, and the perpendicular direction. So I consider this one positive, and I consider that one positive. Okay, so the reason why we do this is because we already have a force in the parallel direction, and when you consider all the forces relative to the plane, resolving the components is much easier. So the components we don't consider the x and y component. We consider the parallel and perpendicular component. All right. So let's talk about number 2 and why it's a shortcut. Okay, so if you make the assumption that it just slides along the plane, so it could either slide down or it could slide up, but it doesn't lift up and it doesn't sink into the plane. Okay, so if you make that assumption, you can assume that the sum of all forces in F, P, E, the perpendicular direction, is equal to 0. Okay, so you literally do not even need to think about anything that's in the perpendicular direction. Okay, so instead, let's just focus on working out what FPA is. Okay, so really, this question is about FR is equal to the sum of FPA. So if this is a little bit confusing, all I'm really saying is that the resultant forces are only going to be in this parallel direction. They're not going to be in the perpendicular direction. Okay, so the parallel direction, let's take a look at these different forces. Okay, so in the parallel direction, if we consider F1, which is part of this equation, F1, it's completely in the parallel direction. So this 5 newtons, we put a negative at the front here because I said this was positive. So because it's in the opposite direction, which is down the plane, it's going to be negative. Okay, so I'm still going to write the components. So I'm going to say FPA just for accuracy. Then I'm going to move on. Okay. Now, if you look at F2, F2 has 30 degrees over here, and it's 30 degrees from the plane. Okay, so if you need to turn this into the parallel component, you imagine this as a triangle, and so I'll just draw some dotted lines to make it a little bit clearer for you as well. If you got, so you want to be working out this component. Now, to work this out, it would be F2, which is 16, and you take cosine because you can imagine this as adjacent and that as the hypotenuse. Okay, so you take cos 30 degrees FPA. And this is the parallel component of F2, okay? And because it's in the positive direction, it's fine to keep it as positive, all right? Now, now we move on to the last force that we have, which is the weight force, okay? So the weight force, if you look at the weight force, it's broken up into these components, okay? So weight force, part of it is in the parallel direction and part of it is in the perpendicular direction. So the parallel direction is actually in the negative direction, which makes sense, right? Because a heavy object on a plane tends to fall down the plane, okay? So it's going to be negative here. So for weight, we're going to put a negative, and when you consider weight, it's always mg. So I'm just going to put mg for now, and I'm going to substitute afterwards. So mg, and whenever you consider the parallel component of the weight force, you always take sine, okay? So you take sine 30 degrees from, and the 30 degrees I'm taking right now is from this 30 degrees of the plane. Sine 30 degrees. And I'm just going to put FPA as well. So in this original equation, we would have to consider the normal force, but the normal force is always in the perpendicular axis, okay? So in this equation, we don't have to think about it because there is no parallel component. There's only a perpendicular component for n, okay? So we are actually done here, and we can start substituting the values, okay? So I'm just going to do -5. So I'm just going to put brackets here. Plus 16 cos 30 degrees minus, it weighs 4 kilograms, g is 9.8, and sine 30. And the reason why I did brackets was because we can just do FPA. It just saves me the hassle of writing FPA over and over again over here on the outside. So FPA really just, it's just there to tell you the direction, okay? Now, the rest of this is just simple calculation through substitution in the calculator. So I'm going to just type -5 plus 16 cos 30 degrees minus 4 times 9.8 times sine 30. And the answer I get is -10.74 newtons, okay? And that is equivalent to 10.74 newtons down the plane, okay? So because I defined positive as being up the plane, being negative means the direction is down the plane, okay? So this is actually a quicker way to do this than breaking down each individual force into parallel and perpendicular components. So because we made the assumption that the block does not jump up, we say the sum of the perpendicular components is 0, and we only need to consider the sum of the parallel components, okay? So that means we completely ignored the normal force. We only had to consider the parallel component of weight force, and then we had to break down F2 into the parallel component. Okay, so 10.74 is the net force, and that is your answer for part A. So now let's move on to part B. Okay, so it's asking what is the acceleration. Okay, so easy. So you know F is equal to ma from Newton's second law, and you just found out that 10.74 is the net force. You know the mass is 4 kilograms, and you were asked to find the acceleration. So therefore, the acceleration is 10.74 divided by 4, which gives me, what's 10.74 divided by 4? I get 2.69 meters per second. Okay? 2.69 meters per second. And let's take a look at C. How fast will it be going after 5 seconds? Okay, after 5 seconds, it is a acceleration question. So you need to be using the what I call it and what my student calls it is called the Suvat equations. Okay, so these come from your syllabus. So I'm just gonna copy this here for convenience. Okay, so all right, so how fast will it be going after 5 seconds? How fast is asking you about velocity. You make the assumption that its initial velocity is 0, and you know the acceleration. So you should be using the first equation, this one. Sorry, I mean the second one. V equals U plus AT. So write the equation first, and then you substitute to follow the conventional method to get the full marks. So you make the assumption that you start at rest, your acceleration is 2.69, and your time is 5 seconds. And your answer should be 2.69 times 5, which is 13.45 meters per second. And you also need a direction, so you write down the plane. All right, so how far does it travel in 8 seconds? So how far is asking you about distance. And to work out distance, you can use either this first equation here or this second equation here. So because we're being asked the distance after 8 seconds, and that's about time, I'm going to be using the first one here. S equals to UT plus half AT squared. So U, again, we make the assumption it has a 0 velocity, and then we have half times A, which is 2.69, and then T squared, which we were told is 8. So plugging this into the calculator, 0.5 times 2.69 times 8 squared, we get 86.08 meters. All right, so that's quite far. And if you look at this example, you might actually think, because there's 16 newtons up this way, you might think this block would be dragged up. But the weight force actually contributes significantly to the down the plane force of this block. So overall, you have a 10.74 net force, and that contributes significantly to the acceleration and the displacement that you eventually get. So I hope this question has been interesting at the very least, and post up any interesting questions you might find in the Dynamics 2 module. Happy to take a look at them. I do some tutoring, and I also help run Prelim Discussion Group 2018. So thanks for watching this video. I'll see you for the next one. Bye for now.